Welcome to the lesson video on linear discriminant analysis and quadratic discriminant analysis. In this lesson video, we're going to talk about these two methods, which are Gaussian maximum likelihood classification methods. And so in Gaussian maximum likelihood classification, we assume each class has a Gaussian distribution, and then we estimate the distributions from the data. Then we classify new observations by assigning them to the class with the maximum likelihood. Now, linear discriminant analysis, or LDA, and quadratic discriminant analysis, or QDA, these are both Gaussian maximum likelihood classification methods. So in this video, we're going to first talk about Gaussian maximum likelihood, and then how it's implemented in these two particular classification methods. So first thing we're going to talk about is likelihood. Likelihood is determined using the probability density function. So here's first is our definition of the probability density function. This should be a familiar formula here. This is the formula for the probability density function for a normal distribution whose mean is mu and whose standard deviation is sigma. And there's a plot in the case mean 0, standard deviation 1. Now, the likelihood function is given by the same formula as the probability density function. And so the likelihood for a value of x of here of about 1.2 we get by just going up to the height of the curve. And you'll notice in some sense we're taking, in likelihood, we're computing the likelihood of these parameters for the distribution given some input value for x. So we look at the probability distribution, which is for x given parameters, and the likelihood is the likelihood for those parameters given x. And so maximum likelihood classification, here's the classification rule. We just assign an observation to x with the class with the greatest likelihood, which is written using the Rmax notation here. And so, for example, if our new observation x has a value of negative 0.5 in the plot on the right-hand side here, then we can look at the likelihood of the blue curve being the curve, the distribution for the data that generated x, and the likelihood for that's about 0.15 or so, going up to the blue curve. We look at the likelihood of the red curve being the distribution that generated x, and that's exceedingly small. So we would say this x should be assigned to class 1, corresponding to the blue curve. Now, if our value is over here at a little bigger than 2, then our likelihood for the red curve is higher because the probability density function for the red curve at that x is higher, and so we'd assign x to 2. And our decision boundary is here where the probability density function curves cross. Everything to the left we'd assign to class 1, everything to the right we would assign to class 2. We can also estimate the probability of being in a class, and so this is probability is given by this formula here, which is generated by Bayes' theorem. I included Bayes' theorem in the bottom left-hand corner of the slide. We're not going to go through how it comes about, but for reference, it's important to know that this formula for the probability is given by Bayes' theorem. And so what's going on here is we have this L, that's the likelihood of the class that we're looking at. So the probability of class K is the likelihood of that class times the prior probability for that class, this pi sub K. Prior probability, remember, has to do with our data and how often that class is represented in the data. So for example, if we had a data set with 2 classes and only 10 observations from one and 1,000 from the other, we would a priori, meaning before we start doing anything or prior to our estimates, we would expect the probability for the class that only has 10 observations to be much smaller. It would be 10 divided by 1,000 plus 10, and so that would be given in that pi sub k. That's the prior probability for that class. And then those two multiplied on the top of this fraction, it's divided by the sum over all classes of the prior probability class times the likelihood for that class. And so let's walk through an example. And this likelihood function, recall, is just the height to the probability density function for that class. And so let's look at that example that we were looking at just a moment ago, and let's compute the probability for class 2 for this observation x. So x is about 2.1. We want to compute the probability that class 2 is the class that's given us this function x, and this is under the assumption that it has to either be from class 1 or class 2. There's no other possibility, and that the prior probabilities for both the classes are the same. So there's no reason before looking at the distributions to expect that one class is more probable than the other, or in other words, our prior probabilities are equal. So to compute the probability for this class, we look at the likelihoods for these two classes, and the likelihood for class 2 in red is 0.15. The likelihood for class 1, shown in blue, is 0.02, and that's these two functions here, which are the height by the arrows next to those two numbers. And now to compute the probability, we use the formula here. This is the probability that y is equal to class 2, or the probability that the correct class for this observation is 2, right? So this is that probability that we're computing. The top of this fraction is the likelihood for the class that we're looking at, so it's the likelihood for class 2 divided by the sums of the likelihoods for all the classes, 0.15 plus 0.02, and that gives us this value of 0.88. So the probability for this class, for class 2, being the class that generated this observation x, is 0.88. And so that's how we compute probabilities for maximum likelihood function classifiers. So let's talk about how we estimate these distributions from the data. So what we did before was assuming we know the distributions. And so what we do for the distributions is we're assuming they're Gaussian or multivariate Gaussian distributions, and so we have standard ways for estimating those. So on the right-hand side, on the left-hand side here, we have two classes, a green and a pink class. This is from figure 4.4 in the textbook, Isler. And we take random samples from those two classes, which are shown in histograms on the right-hand side. We compute the mean and standard deviation for each of those random samples. And then the place where the distributions cross, or the likelihoods are equal, are given by this dark black line. And then in the dotted line, that's where the Bayes optimal decision boundary is. Bayes optimal decision boundary is on the left-hand side, exactly where the two distributions cross. The black straight line is where the distributions that are estimated from the data cross. Okay, so that's estimating distributions from the data, and that's pretty familiar for single variable distributions. So let's talk a little bit about multivariate Gaussian normal distribution. So in the two plots here, the two three-dimensional plots, we have two multivariate Gaussian normal distributions. Instead of a bell curve in one dimension, think about these as giving you a bell curve in multiple dimensions. The formulas are shown here for the probability density functions. You'll notice both of them, the familiar single variable one and the which may be familiar multivariate Gaussian distribution. They both have a term times an exponential function, and then in the top of the exponential function, there's something that's acting like a normalized distance to the mean, and we'll talk about that in a moment. But to understand these probability density functions, let's think about what the contour plots are. So the two plots, these two axes that are above our three-dimensional plots, we're going to draw the contour plots. So for the plot on the left, if we look at contour plot, when we say contour plot, we mean if we took this plot and we cut it at a fixed height, what would the contour be when we plot it in just the two variables? So the contour plot here would be a circle, and then if we go down, further down in the height, we'd get a circle that's farther out, and then a larger concentric circle. So we would get a series of concentric circles. If we were to look at contour plots on the plot on the right, it would look like that. And so we would get these ellipsoids. And so this is a good way to think about multivariate normal distributions, that there are these concentric circles or concentric ellipsoids that tell you how far away you are from the mean, and inside of these circles is where you're going to get more of your data, or your data point that's a random sample, randomly drawn from this distribution is more likely to be towards the inner circle or the inner side of the ellipse. This function in the top of the exponential here, in the single variable case, this is called a z-score. If you take the square root of that portion of that top function, right, it's a distance from the mean squared divided by the variance squared. Take the square root of that gives you a z-score. In the multivariate case, this is called the Mahalanobis distance. And if you look at the form of these functions, they each have something that acts like a mean minus the mu squared, or times itself, and then a piece which is acting like a variance, or in the single variable, we're dividing by the variance. In the multivariate, we're taking the matrix inverse of that sigma, which is the covariance matrix. Getting into how that's computed is a little bit beyond what we're going to talk about in this course. We're just taking a look at the math a little bit underneath the hood to get some sort of intuition for what's going on. And so here's the formula for computing that covariance matrix, and the formula for the multivariate normal distribution. And so on the left-hand side, we have a multivariate normal distribution, the mean shown, and it has a shape that you can see that's where the level sets would be ellipsoids. And if you look at one of those contours, that ellipsoid, that corresponds to a fixed Mahalanobis distance away from the mean. So if you computed the distance from the mean out to that ellipsoid using the Mahalanobis distance, it would be equal for every point on that ellipse. And the Mahalanobis distance, recall previous slide, is given by this formula up here. It's that term in the top part of the exponential. Okay, and another thing about that ellipsoid, we won't be using this, but there are estimates for how much data should be inside that ellipsoid depending on the size of the Mahalanobis distance. So the Mahalanobis distance has a chi-square distribution, which depends on your dimensions of your data. So you can pick a Mahalanobis distance so that, say, 50% of your data, maybe, in this example, would be inside there. Or you can go out further and say 95% of your data maybe is within a further Mahalanobis distance, maybe represented by that larger ellipsis. So when we think of a multivariate Gaussian distribution, we can think of these ellipsoids that contain larger and larger amounts of the data that roughly correspond. You can think about them as standard deviations away from the mean, but instead of just a standard deviation plus or minus some amount from the mean, it's an ellipsoid containing data instead of an interval. Okay, so moving on to the LDA and QDA methods, so both linear discriminant analysis and quadratic discriminant analysis. First step is we assume each class in our data set has an underlying Gaussian distribution. In LDA, we're going to add an additional assumption that every covariance is the same. And so that's this assumption that's present in LDA, but not present in QDA. In QDA, we assume our different classes can have different covariances. Third step in the same as the both, and it's the second step in QDA and third step in LDA. We're going to estimate the covariance and the means from the data. And I guess the only difference here in QDA, we have to estimate the covariance of each class, where in LDA, we're just estimating one covariance. That makes a difference if you don't have a lot of data. If you don't have a lot of data, it's easier to estimate one covariance when you're doing LDA, versus QDA, you have to estimate multiple covariances. You can get bad estimates for your covariances if you don't have sufficient data. And then the last step for both of these is how we do our classification, and the classification is done the same way. We just assign each new observation to the class with the greatest likelihood. The greatest likelihood is the value of the probability density function given by that by the likelihood formula that we saw before. In LDA, this corresponds to the class that you are closest to the mean using Mahalanobis distance. It's not quite as simple. You can't use the Mahalanobis distance with QDA because you have different Gaussians. So let's take a look at how this looks on some data. This is some data using handwritten digits. A bunch of digits, a handwriting of 1, a bunch of number 2s handwritten, number 3s. It's in 256 dimensions, and we're showing this lower dimensional, two-dimensional plot on the left-hand side. These are the class separations shown in purple for the linear discriminant analysis. And on the right-hand side, we get class separations using QDA. And you can see here that these three classes have very different distributions, and QDA seems to be doing better. It seems to fit those distributions. So what I'm talking about, let's be a little detailed. If I were going to try to look at let's see, the 3, it'd come up better if I should do it in red. So maybe the mean of the class of 3s is somewhere about there. And if I were to estimate the distribution using a multivariate linear distribution for the 3s, I might get something like that. And if I was going to estimate where the mean of the 1s are, the mean of the 1 class is there, and maybe I'm just drawing and sketching, but the covariance might be represented by that. And then for the 2s, maybe there's the mean for the 2s, and the covariance matrix, if we're going to look at the distribution for the 2s, it would look like that. And so what we see just from sketching and thinking about the geometry, that we have what appear to be 3 different covariances, and QDA seems to be doing a better job giving us separations between these classes, where we can see the separations seem to be quadratic or parabola-like instead of the linear LDA separations. So, review for what we've talked about today. LDA and QDA both assume that each of our classes in our data are given by Gaussian distributions. They estimate those distributions from the data, and they classify by maximum likelihood. And this figure on the top right-hand side is a good way to remember LDA. We have 3 classes given by normal distributions, two variable normal distributions in this case. On the left-hand side, we represent those distributions. On the right-hand side, we generate data and estimate the class separation for those distributions. The difference between LDA and QDA: LDA assumes that all the classes have the same distribution. QDA allows the classes to have different distributions. And with LDA, we're always going to get linear planes or hyperplanes or lines that are decision boundaries between our classes. In QDA, we're always going to get a quadratic, parabola-like decision boundary or second-order polynomial formulas for those decision boundaries. Thank you very much.